Hello everyone, I'm Professor Diwa, and welcome to a math video on exponential functions. Our objectives are to graph exponential functions, solve equations of the form b to the x equals b to the y, solve problems modeled by exponential equations. Okay, so let's get started. First, we have the definition for an exponential function. It states here that a function of the form f of x equals b to the x power is called an exponential function, where b is greater than 0, b is not 1, and x is a real number. In the next set of examples, we're going to graph exponential functions of this form, as well as solve exponential equations. In example number 1, graph the exponential functions. For part A, we have f of x equals 2 to the x power, and for part B, we have g of x equals 1/2 raised to the x power. To graph these functions, we're going to use the point plotting method. So below we have an x and y chart. The x values I'm going to use for both functions is going to be -2, -1, 0, 1, and 2. Next, we're going to find the corresponding y values, starting with the function f. We take -2 and plug it into the function f. We get 2 to the -2 power is equal to 1/4. For -1, we get 2 to the -1 power equals 1/2. For 0, we get 2 to the 0 power is equal to 1. For 1, we have 2 to the 1 power is equal to 2. For 2, we have 2 squared is equal to 4. Next, we're going to go ahead and plot each one of these points. -2, 1/4 would be here, -1, 1/2 is here, 0, 1 is right here, 1, 2 is plotted over here, and 2, 4 is right here. Next, we draw a curve through our points. Now we have the graph of f of x in red. Starting on the bottom left, you could see that the graph of f starts off really close to the x-axis, however it actually doesn't touch it. And as the x values increase, the graph starts slowly increasing. It's not until we get past the value of 0 that our graph starts rapidly increasing. This type of growth described by this graph is what we call exponential growth. We get exponential growth whenever the base of the exponent b is a value greater than 1. In our case for the function f, our value of b is equal to 2, which resulted in exponential growth. Next, we're going to move on to part b. We have g of x equals 1/2 to the x power. We're going to continue filling in our xy chart using the same x values. Starting with the x value of -2, we plug that into the function g. We get 1/2 to the -2 power equals 4. For -1, we get 1/2 to the -1 power equals 2. For 0, we get 1/2 to the 0 power is equal to 1. For 1, we get 1/2 to the 1 power is equal to 1/2. For 2, we get 1/2 squared is equal to 1/4. Next, we're going to go ahead and plot each one of these points. So we have -2, 4 here, -1, 2 is over here, 0, 1 is here, 1, 1/2 is over here, and 2, 1/4 is over here. Next, we draw a curve through our points, and now we have the graph of g in blue. Notice here that our graph starts off really high and starts decreasing rapidly as the x values get larger and larger. Notice towards the end that the graph gets really close to the x-axis, however it never touches. This type of growth is what we call exponential decay. This takes place whenever the base of the exponent b is a value between 0 and 1. For our function g, the value of b is 1/2, so we have exponential decay. One more thing I want to point out is that we have a horizontal line going across the x-axis. This horizontal line is what we call an asymptote. The asymptote is not part of the graph, but we use it as a guide to help us sketch the graph of exponential functions. Next, we have a practice problem. Graph the exponential functions. For part A, we have f of x equals 3 to the x power. For part B, we have g of x equals 1/3 raised to the x power. Alright, so go ahead and pause the video, graph each function, and then check back with the video to see the solutions. Alright, so let's go over the solutions. First, we're going to fill in the x and y chart for f of x and g of x. For the x values, we're using the same values of -2, -1, 0, 1, and 2 for both graphs. Starting with -2, we plug that into the function f. We get 3 to the -2 power equals 1 over 9. For -1, we get 3 to the -1 power equals 1 over 3. For 0, we get 3 to the 0 power equals 1. For 1, we have 3 to the 1 power equals 3. For 2, we get 3 squared equals 9. Next, we're going to fill in the values for g of x. Starting with the x value of -2, we plug it into the function g. We get 1/3 raised to the -2 power equals 9. For -1, we get 1/3 raised to the -1 power equals 3. For 0, we get 1/3 raised to the 0 power is 1. For 1, 1/3 raised to the 1 power equals 1/3. For 2, we get 1/3 squared is equal to 1 over 9. Next, we plot the points for the function f. We have -2, 1/9 over here, -1, 1/3 is here, 0, 1 is here, 1, 3 is here, and 2, 9 is over here. Next, we draw the curve through our points, and now we have the graph of the function f in red. Next, we plot the points for the function g. We have -2, 9 here, -1, 3 here, 0, 1 is plotted over here, 1, 1/3 is over here, and finally we have 2, 1/9 over here. Next, we draw the curve through our points, and now we have our graph for the function g in blue. In example number 2, graph the exponential functions. For part A, we have f of x equals 2 raised to the x plus 3 power. For part B, we have g of x equals 3 raised to the x plus 2 power. Starting off with part A, we're going to graph this function using the point plotting method. Below, we have an x and y table for the function f and the function g. For both of these functions, we're going to use the x values of -4, -3, -2, -1, and 0. We just need to fill in the corresponding y values. Starting with the function f, we're going to take our x value of -4 and plug it into the function. We get 2 to the -4 plus 3 power. When we simplify this, we get 2 to the -1 power, which is equal to 1/2. Next, we have -3. We get 2 to the -3 plus 3 power. This simplifies to 2 to the 0 power, which is equal to 1. For -2, we get 2 to the -2 plus 3 power, which simplifies to 2 to the 1 power, which is equal to 2. For -1, we get 2 to the -1 plus 3 power, which simplifies to 2 squared, which is equal to 4. For 0, we get 2 to the 0 plus 3 power, which simplifies to 2 cubed. This is equal to 8. Next, we go ahead and plot each point. We have -4, 1/2 is here, -3, 1 is here, -2, 2 is over here, -1, 4 is here, and 0, 8 is plotted over here. Next, we draw a curve through our points. Now we have the graph of the function f of x in red. If we compare this graph to the graph of 2 to the x power, you can see that they have the same exact shape, except for our graph of 2 to the x plus 3 power is shifted over to the left. If we take a look at the point 0, 1 on the graph of 2 to the x power, you can see that the corresponding point on the other graph is shifted 3 spaces over to the left. If we take a look at all the other points, you'll see that the corresponding points on the other graph are all shifted 3 spaces to the left. So the +3 in the exponent shifts the graph 3 spaces in the left direction. Now if this was a -3, this would shift our graph 3 spaces in the right direction. Now let's move on to part B. We have g of x equals 3 to the x plus 2 power. Now without graphing this function, I could see that we have a value of 3 for the base b. Since this value is greater than 1, this results in a graph with exponential growth. Also, because we have a +2 in the exponent, this means that our graph is going to have the same exact shape as 3 to the x power, except that our graph is going to be shifted 2 spaces to the left. Alright, So let's go ahead and fill in our chart. Starting with -4, we're going to plug that into the function g. We get 3 to the -4 plus 2 power simplifies to 3 to the -2 power. This is equal to 1 over 9. For -3, we get 3 to the -3 plus 2 power, which simplifies to 3 to the -1 power. This is equal to 1 over 3. Next we have -2. 3 to the -2 plus 2 power simplifies to 3 to the 0 power, which is equal to 1. For -1, we get 3 to the -1 plus 2 power, which simplifies to 3 to the 1 power, which is equal to 3. For 0, we get 3 to the 0 plus 2 power, which simplifies to 3 squared. This is equal to 9. Next, we go ahead and plot each point. We have -4, 1/9 over here, -3, 1/3 over here, -2, 1 is over here, -1, 3 is over here, and 0, 9 is over here. Next, we draw a curve through our points, and now we have the graph of g of x in blue. Next, we have the uniqueness of b to the x power. Here it states let b be greater than 0 and b not equal to 1. Then b to the x power is equal to b to the y power is equivalent to x equals y. This is a property of exponents which we use to solve exponential equations. When the bases of the exponents are the same, we can drop the base and set the exponents equal to each other. In the next example, I'll show you how we apply the uniqueness property. In example number 4, solve each equation for x. For part A, we have 2 to the x power equals 16. In order to solve for x, we need to rewrite 16 as an exponent with the base of 2. This would be 2 to the 4th power. So we have 2x equals 2 to the 4th power. Now that the bases of the exponent are the same, we can apply the uniqueness property of exponents. So we can drop the bases and set the exponents equal to each other. We get x equals 4. Next, we write our final answer in set notation. We have a set of curly brackets and 4 on the inside. Moving on to part B, we have 9 to the x power equals 27. Now it's not possible to rewrite 27 as an exponent with a base of 9, so we're going to have to rewrite 9 as an exponent. 9 as an exponent would be 3 squared, and now we can rewrite 27 as an exponent with the base of 3, which is 3 cubed. So we have parentheses 3 squared and an exponent of x on the parentheses equals 3 cubed. From here we can multiply the exponents of 2 and x. This would just be 2x. So the result is 3 raised to the exponent of 2x equals 3 cubed. Now that the bases are the same, we can apply the uniqueness property of exponents to drop the bases and set the exponents equal to each other. We get 2x equals 3, and now we just need to solve for x. We need to get rid of the 2 by dividing both sides by 2. We get 2x divided by 2 equals 3 over 2. After simplifying, we get x equals 3 over 2. Next, we need to write our final answer in set notation, have a set of curly brackets, and 3 over 2 on the inside. Moving on to part C, we have 4 to the x plus 3 power equals 8 to the x power. Since we can't rewrite 8 as an exponent with a base of 4, we're going to need to rewrite 4 as an exponent. This would be 2 squared. Now we could rewrite 8 as an exponent with a base of 2, which would be 2 cubed. So we have parentheses 2 squared raised to the x plus 3 power equals parentheses 2 cubed raised to the x power. Next, we could simplify by multiplying the exponents together. So we have 2 times x plus 3 is 2x plus 6, and 3 times x is 3x. The result is 2 to the 2x plus 6 power equals 2 to the 3x power. Next, we apply the uniqueness property of exponents. We get 2x plus 6 equals 3x. From here, we need to move all the x variables to one side of the equation, so I subtracted 2x from both sides. The result is 6 equals x, and now we write our final answer in set notation, which is a set of curly brackets and 6 on the inside. Moving on to part D, we have 5 to the x power equals 10. For this problem, we can't rewrite 10 as an exponent with a base of 5, and we can't rewrite 5 as an exponent with a smaller base. In this case, we need to use a graphing calculator to solve this problem. So on the graphing calculator, you want to go to your equation editor. So we need to press the y equals button in the top left corner. Next, we need to enter 5 to the x power for y1 and enter 10 for y2. Once we have everything entered in, we could go ahead and hit the graph button in the top right corner to graph both equations. So here you can see we have the graph for both of our equations. y1 equals 5 to the x power is the graph in blue, and y2 equals 10 is the horizontal line going across the top of our screen. What we need to do here is find the intersection of both of these graphs. Hit the blue button, which is the second button up here, and then hit Trace, which will bring you to the Calculate menu. Under the Calculate menu, you want to choose number 5, which is Intersect. Next, your graphing calculator is going to ask you which one is the first curve. The first curve should already be highlighted, so just hit Enter. Next, the calculator will ask you to identify the second curve. The cursor should have already jumped or moved over to the second curve, so just hit Enter. Next, you want to move the cursor over to the point of intersection. It doesn't need to be exactly on the intersection, just close, and then press Enter. Now we have the solution in the bottom corner. It says x is equal to 1.4306766, and this decimal value actually keeps on going. For this problem, we're going to round our answer to 2 decimal places. So we have x equals 1.43, and our final answer we write in set notation. So I have a set of curly brackets and 1.43 on the inside. Next, we have a practice problem. Solve each equation for x. For part A, we have 3 to the x power equals 9. For part B, we have 8 to the x power equals 16. For part C, we have 125 to the x power equals 25 to the x minus 2 power. For part D, we have 7 to the x power equals 21. Alright, so go ahead and pause the video, solve each equation for x, and then check back with the video to see the solutions. Alright, so let's go over part A. First, we need to rewrite 9 to have a base of 3. This would be 3 squared. So we have 3 to the x power equals 3 squared. Next, we apply the uniqueness property of exponents. We get x equals 2. So our final answer in set notation would be a set of curly brackets and 2 on the inside. For part B, we need to rewrite 8 as an exponent with a base of 2, so this would be 2 cubed, and we could rewrite 16 as 2 to the 4th power. So we have parentheses 2 cubed raised to the x power equals 2 to the 4th power. Next, we can multiply the exponents together. 3 times x is 3x, so we have 2 to the 3x power equals 2 to the 4th power. Next, we apply the uniqueness property of exponents. We get 3x equals 4, and now we need to solve for x by getting rid of the 3. We just divide both sides by 3. We get 3x over 3 equals 4 over 3. After simplifying, we get x equals 4 over 3. Next, we write our final answer in set notation. So I have curly bracket 4 over 3 close curly bracket. Moving on to part C, we need to rewrite 125 as 5 cubed and 25 as 5 squared. We have parentheses 5 cubed raised to the x power equals parentheses 5 squared raised to the x minus 2 power. Next, we multiply the exponents together. 3 times x is 3x, and 2 times x minus 2 is 2x minus 4. So the result is 5 to the 3x power equals 5 to the 2x minus 4 power. From here, we apply the uniqueness property of exponents. We get 3x equals 2x minus 4. Next, we need to move the x variables onto the same side, so I subtracted 2x from both sides of the equation. The result is x equals negative 4. Now we can write our final answer in set notation, so I have a set of curly brackets and negative 4 on the inside. Moving on to part D, it's not possible to rewrite 21 as an exponent with a base of 7, and it's not possible to rewrite 7 as an exponent with a smaller base. In this case, you need to use a graphing calculator to solve this problem. So for this problem, after rounding to 2 decimal places, I got that x is approximately equal to 1.56. So the final answer in set notation is curly bracket 1.56 close curly bracket. Next, we have the compound interest rate formula, which is capital A equals capital P times the parentheses 1 plus r over n raised to the nt power. Capital P equals the principal or the amount of a loan, r equals the annual interest rate, n equals the number of times interest is compounded each year, t equals the duration of the loan in years. In example number 5, use the compound interest formula to find the following. Find the amount owed at the end of 5 years if $1,600 is loaned at a rate of 9% compounded monthly. To solve this problem, we just use the compound interest formula and plug in the values for P, R, N, and T. The value for P is going to be $1,600. The value for R is going to be 9% or 0.09. The value for N is the number of compoundings per month, which is monthly or 12. The value for T is 5. We get A equals 1600 times the parentheses 1 plus 0.09 over 12 raised to the 12 times 5 power. Next, we simplify. On the inside of the parentheses, I can divide 0.09 by 12 and add 1. This would be 1.0075. We could also simplify the exponent. 12 times 5 is 60. So we get 1600 times the parentheses 1.0075 raised to the 60th power. Next, we could simplify using a calculator. We just take 1.0075 and raise it to the 60th power. Afterwards, we multiply it by 1600. The result is 2505.089643, and this decimal value keeps on going. After rounding this value to 2 decimal places, we get our final answer, which is $2,505.09 will be owed at the end of 5 years. In example number 6, as a result of the Chernobyl nuclear accident, radioactive debris was carried through the atmosphere. One immediate concern was the impact that the debris had on the milk supply. The percent Y of radioactive material in raw milk after T days is estimated by the equation Y equals 100 times the parentheses 2.7 raised to the negative 0.1 T power. Estimate the expected percent of radioactive material in the milk after 30 days. To estimate the expected percentage of radioactive material after 30 days, we just need to use the equation they gave us and substitute the value of 30 in for T. We get Y equals 100 times the parentheses 2.7 raised to the negative 0.1 times 30 power. We could just simplify by using a calculator. The result is 5.080526, and this decimal value keeps on going. For this problem, I rounded to the nearest whole number, which is 5. For the final answer, I stated that there is 5% radioactive material in the milk after 30 days. Alright, so we reached the end of our video. Thank you very much for watching. I'm Professor Diwa, and I'll see you in the next one.